In automotive design, the automobile layout describes where on the vehicle the engine and drive wheels are found. Many different combinations of engine location and driven wheels are found in practice, and the location of each is dependent on the application for which the vehicle will be used. Factors influencing the design choice include cost, complexity, reliability, packaging, weight distribution, and the vehicle's intended handling characteristics. Layouts can roughly be divided into two categories, front or rear-wheel drive. Four-wheel drive vehicles may take on the characteristics of either, depending on how power is distributed to the wheels. Front-wheel drive layouts. Front-wheel drive layouts are those in which the front wheels of the vehicle are driven. The most popular layout used in cars today is the front engine, front-wheel drive, with the engine in front of the front axle, driving the front wheels. This layout is typically chosen for its compact packaging. Since the engine and driven wheels are on the same side of the vehicle, there is no need for a central tunnel through the passenger compartment to accommodate a prop shaft between the engine and the driven wheels. As the steered wheels are also the driven wheels, FF cars are generally considered superior to FR cars in conditions such as snow, mud, or wet tarmac. The weight of the engine over the driven wheels also improves grip in such conditions. However, powerful cars rarely use the FF layout because weight transference under acceleration reduces the weight on the front wheels and reduces their traction, limiting the torque which can be utilized. Electronic traction control can avoid wheel spin but largely negates the benefit of extra torque power. A transverse engine is commonly used in FF designs, in contrast to FR which uses a longitudinal engine. The FF layout also restricts the size of the engine that can be placed in modern engine compartments, as FF configurations usually have inline 4 and V6 engines, while longer engines such as inline 6 and 90° V8 will rarely fit. This is another reason luxury sports cars avoid the FF layout. Exceptions do exist, such as the Volvo S80 which uses transversely mounted inline 6 and V8 engines, and the Ford Taurus SHO, available with a 60° V8 and front-wheel drive. Characteristics front-wheel drive gives more interior space since the powertrain is a single unit contained in the engine compartment of the vehicle and there is no need to devote interior space for a drive shaft tunnel or rear differential, increasing the volume available for passengers and cargo. There are some exceptions to this as rear engine designs do not take away interior space. It also has fewer components overall and thus lower weight. The direct connection between engine and transaxle reduces the mass and mechanical inertia of the drivetrain compared to a rear-wheel drive vehicle with a similar engine and transmission, allowing greater fuel economy. In front-wheel drive cars the mass of the drivetrain is placed over the driven wheels and thus moves the center of gravity farther forward than a comparable rear-wheel drive layout, improving traction and directional stability on wet, snowy, or icy surfaces. Front-wheel drive cars, with a front-weight bias, tend to understeer at the limit which, according to Saab engineer Gunnar Larsson, is easier since it makes instinct correct in avoiding terminal oversteer, and less prone to result in fishtailing or a spin. According to a sales brochure for the 1989 Lotus Elan, the ride and handling engineers at Lotus found that for a given vehicle weight, power and tire size, a front-wheel drive car was always faster over a given section of road. However, this may only apply for cars with moderate power-to-weight ratio. According to road test with two Dodge Daytonas, one FWD and one RWD, the road layout is also important for what configuration is the fastest. Weight shifting limits the acceleration of a front-wheel drive vehicle. During heavy acceleration, weight is shifted to the back, improving traction of the rear wheels at the expense of the front driving wheels. Consequently, most racing cars are rear-wheel drive for acceleration. However, since front-wheel drive cars have the weight of the engine over the driving wheels, the problem only applies in extreme conditions in which case the car understeers. On snow, ice, and sand, rear-wheel drive loses its traction advantage to front or all-wheel drive vehicles which have greater weight over the driven wheels. Rear-wheel drive cars with rear engine or mid-engine configuration retain traction over the driven wheels, although fishtailing remains an issue on hard acceleration while in a turn. Some rear-engine cars can suffer from reduced steering ability under heavy acceleration, since the engine is outside the wheelbase and at the opposite end of the car from the wheels doing the steering. A rear-wheel drive car's center of gravity is shifted rearward when heavily loaded with passengers or cargo, which may cause unpredictable handling behavior. On FR cars, the long drive shaft adds to drivetrain elasticity. Advantages interior space. Since the powertrain is a single unit contained in the engine compartment of the vehicle, there is no need to devote interior space for a drive shaft tunnel or rear differential, increasing the volume available for passengers and cargo. Instead, the tunnel may be used to route the exhaust system pipes. Weight. Fewer components usually means lower weight. Improved fuel efficiency due to less weight. Cost. Fewer material components and less installation complexity overall. However, the considerable MSRP differential between a FF and FR car cannot be attributed to layout alone. The difference is more probably explained by production volumes, as most rear-wheel cars are usually in the sports or luxury categories, while the FF configuration is typically in mass-produced mainstream cars. Few modern family cars have rear-wheel drive as of 2009, so a direct cost comparison is not necessarily possible. A contrast could be somewhat drawn between the Audi A4 front track and a rear-wheel drive BMW 3 Series, both which are in the compact executive car classification. Improved drivetrain efficiency. The direct connection between engine and transaxle reduce the mass and mechanical inertia of the drivetrain compared to a rear-wheel drive vehicle with a similar engine and transmission, allowing greater fuel economy. Assembly efficiency. The powertrain can often be assembled and installed as a unit, which allows more efficient production. Placing the mass of the drivetrain over the driven wheels moves the center of gravity farther forward than a comparable rear-wheel drive layout, improving traction and directional stability on wet, snowy, or icy surfaces. Predictable handling characteristics. Front-wheel drive cars, with a front weight bias, tend to understeer at the limit, which is easier since it makes instinct correct in avoiding terminal oversteer, and less prone to result in fishtailing or a spin. A skilled driver can control the movement of the car even while skidding by steering, throttling and pulling the handbrake. It is easier to correct trailing throttle or trailing brake oversteer. The wheelbase can be extended without building a longer drive shaft. Disadvantages. Front-engine front-wheel drive layouts are nose-heavy with more weight distribution forward, which makes them prone to understeer, especially in high-horsepower applications. If a front-engine front-wheel drive layout is fitted with a four-wheel drive, plus enthusiast driver aids, such as active front differential, active steering, and ultra-quick electrically adjustable shocks, this somewhat negate the understeer problem and allow the car to perform as well as a front-engine rear-wheel drive car. These trick differentials, which are found on the Acura TL WD and Audi S4 3.0 TFSI Quattro, and Audi RS5 4.2 FSI Quattro, are heavy, complex, and expensive. While these aids do tame front-end plow, cars fitted with these systems are still at a disadvantage when track-tested against rear-wheel drive vehicles. Torque steer is the tendency for some front-wheel drive cars to pull to the left or right under hard acceleration. It is a result of the offset between the point about which the wheel steers and the centroid of its contact patch. The tractive force acts through the centroid of the contact patch, and the offset of the steering point means that a turning moment about the axis of steering is generated. In an ideal situation, the left and right wheels would generate equal and opposite moments, cancelling each other out. However, in reality, this is less likely to happen. Torque steer can be addressed by using a longitudinal layout, equal-length drive shafts, half shafts, a multilink suspension or center-point steering geometry. In a vehicle, the weight shifts back during acceleration, giving more traction to the rear wheels. This is one of the main reasons nearly all racing cars are rear-wheel drive. However, since front-wheel drive cars have the weight of the engine over the driving wheels, The problem only applies in extreme conditions such as attempting to accelerate up a wet hill or attempting to beat another RWD car off the line. In some towing situations, front-wheel drive cars can be at a traction disadvantage since there will be less weight on the driving wheels. Because of this, the weight that the vehicle is rated to safely tow is likely to be less than that of a rear-wheel drive or four-wheel drive vehicle of the same size and power. Traction can be reduced while attempting to climb a slope in slippery conditions such as snow or ice-covered roadways. Due to geometry and packaging constraints, the CV joints attached to the wheel hub have a tendency to wear out much earlier than the universal joints typically used in their rear-wheel drive counterparts. The significantly shorter drive axles on a front-wheel drive car causes the joint to flex through a much wider degree of motion, compounded by additional stress and angles of steering, while the CV joints of a rear-wheel drive car regularly see angles and wear of less than half that of front-wheel drive vehicles. Turning circular Euro FF layouts almost always use a transverse engine installation, which limits the amount by which the front wheels can turn, thus increasing the turning circle of a front-wheel drive car compared to a rear-wheel drive one with the same wheelbase. A notable example is the original Mini. It is widely misconceived that this limitation is due to a limit on the angle at which a CV joint can be operated, but this is easily disproved by considering the turning circle of car models that use a longitudinal FF or F4 layout from Audi and Saab. The FF transverse engine layout restricts the size of the engine that can be placed in modern engine compartments, so it is rarely adopted by powerful luxury and sports cars. FF configurations can usually only accommodate inline-4 and V6 engines, while longer engines such as inline-6 and 90-degree big-bore V8 will rarely fit, though there are exceptions. One way around this problem is using a staggered engine. It makes heavier use of the front tires, causing more wear in the front than in a rear-wheel drive layout. Under extreme braking, the already front-heavy layout further reduces traction to the rear wheels. This results in disproportionate gripping forces focused at the front while the rear does not have enough weight to effectively use its brakes. Because the rear tire's capabilities in braking are not very high, a significant number of cheaper front-drive vehicles use drum brakes in the rear even today. The steering feel is more numbed than a WD car. This is due to the extra weight of drive shafts and CV joint components that increase unsprung weight. Rear-wheel drive layouts. Rear-wheel drive typically places the engine in the front of the vehicle and the driven wheels are located at the rear, a configuration known as front engine, rear-wheel drive layout. The front mid-engine, rear mid-engine and rear engine layouts are also used. This was the traditional automobile layout for most vehicles up until the 1970s and 1980s. Nearly all motorcycles and bicycles use rear-wheel drive as well, either by driveshaft, chain, or belt, since the front wheel is turned for steering, and it would be very difficult and cumbersome to bend the drive mechanism around the turn of the front wheel. A relatively rare exception is with the moving bottom bracket type of recumbent bicycle, where the entire drivetrain, including pedals and chain, pivot with a steering front wheel. Characteristics equals, the vast majority of rear-wheel drive vehicles use a longitudinally mounted engine in the front of the vehicle, driving the rear wheels via a drive shaft linked via a differential between the rear axles. Some F layout vehicles place the gearbox at the rear, though most attach it to the engine at the front. The F layout is often chosen for its simple design and good handling characteristics. Placing the drive wheels at the rear allows ample room for the transmission in the center of the vehicle and avoids the mechanical complexities associated with transmitting power to the front wheels. For performance-oriented vehicles, the F layout is more suitable than front-wheel drive designs, especially with engines that exceed 200 horsepower. This is because weight transfers to the rear of the vehicle during acceleration, which loads the rear wheels and increases their grip. Another advantage of the F layout is relatively easy access to the engine compartment, a result of the longitudinal orientation of the drivetrain, as compared to the FF layout. Powerful engines such as the inline-6 and 90-degree big-bore V8 are usually too long to fit in a FF transverse engine layout. The FF configuration can typically accommodate at the maximum an inline-4 or V6. This is another reason luxury sports cars almost never use the FF layout. Advantages even weight distribution. The layout of a rear-wheel drive car is much closer to an even fore and aft weight distribution than a front-wheel drive car, as more of the engine can lie between the front and rear wheels, and the transmission is moved much farther back. Weight transfer during acceleration. During heavy acceleration, weight is placed on the rear, or driving wheels, which improves traction. No torque steer. Steering radius. As no complicated drive shaft joints are required at the front wheels, it is possible to turn them further than would be possible using front-wheel drive, resulting in a smaller steering radius for a given wheelbase. Better handling at the hands of an expert. The more even weight distribution and weight transfer improve the handling of the car. The front and rear tires are placed under more even loads, which allows for more grip while cornering. Better braking. The more even weight distribution helps prevent lock-up from the rear wheels becoming unloaded under heavy braking. Towing. Rear-wheel drive puts the wheels which are pulling the load closer to the point where a trailer articulates, helping steering, especially for large loads. Serviceability. Drivetrain components on a rear-wheel drive vehicle are modular and do not involve packing as many parts into as small a space as does front-wheel drive, thus requiring less disassembly or specialized tools in order to service the vehicle. Robustness. Due to geometry and packaging constraints, the universal joints attached to the wheel hub have a tendency to wear out much later than the CV joints typically used in front-wheel drive counterparts. The significantly shorter drive axles on a front-wheel drive car causes the joint to flex through a much wider degree of motion, compounded by additional stress and angles of steering, while the CV joints of a rear-wheel drive car regularly see angles and wear of less than half that of front-wheel drive vehicles. Can accommodate more powerful engines as a result of the longitudinal orientation of the drivetrain, such as the inline-6, 90-degree big-bore V8. V10 and V12, making the FR a common configuration for luxury and sports cars. These engines are usually too long to fit in a FF transverse engine layout. The FF configuration can typically accommodate at the maximum an inline-4 or V6. Road grip feedback. Front wheels are not affected by engine and gearbox, thus allowing for better feeling of tire grip on road surface. Disadvantages. Under heavy acceleration, oversteer and fishtailing may occur as the rear wheels break free and spin. The corrective action is to let off the throttle. On snow, ice and sand, rear-wheel drive loses its traction advantage to front or all-wheel drive vehicles, which have greater weight on the driven wheels. This issue is particularly noticeable on pickup trucks, as the weight of the engine and cab will significantly shift the weight from the rear to the front wheels. Rear-wheel drive cars with rear-engine or mid-engine configuration do not suffer from this, although fishtailing remains an issue. To correct this situation, owners of RWD vehicles can load sandbags in the back of the vehicle in order to increase the weight over the rear axle, however speeds should be restricted to correctly predicted available grip of the road. Some rear-engine cars can suffer from reduced steering ability under heavy acceleration, because the engine is outside the wheelbase and at the opposite end of the car from the wheels doing the steering, although the engine weight over the rear wheels provides outstanding traction and grip during acceleration. Decreased interior space. Though individual designs vary greatly, rear-wheel drive vehicles may have less front leg room as the transmission tunnel takes up a space between the driver and front passenger, less leg room for center rear passengers, and sometimes less boot space. Rear-engine designs do not inherently take away interior space. A rear-wheel drive vehicle with four-wheel drive, compared to a front-wheel drive vehicle with four-wheel drive, will have a less efficient interior packaging since the transmission is often under the front passenger compartment between the two seats, whereas the latter can package all the components under the hood. Increased weight. The components of a rear-wheel drive vehicle's powertrain are less complex, but they are larger. The drive shaft adds weight. There is extra sheet metal to form the transmission tunnel. There is a rear axle or rear half shafts, which are typically longer than those in a front-wheel drive car. A rear-wheel drive car will weigh slightly more than a comparable front-wheel drive car. rear-biased weight distribution. When loaded, a rear-wheel drive car's center of gravity is shifted rearward when heavily loaded with passengers or cargo, which may cause unpredictable handling behavior at the hands of an inexperienced driver. It needs to be noted that rear-engine cars are by their very nature, rear-weight biased. Higher initial purchase price. Modern rear-wheel drive vehicles are typically more expensive to purchase than comparable front-wheel drive vehicles. Part of this can be explained by the added cost of materials and increased labor put into assembly of Ff layouts, as the powertrain is not one compact unit. However, the difference is more probably explained by production volumes, as most rear-wheel cars are usually in the sports or luxury categories, while the FF configuration is typically in mass-produced mainstream cars. The possibility of a slight loss in the mechanical efficiency of the drivetrain. Cars with rear-engine or mid-engine configuration and a transverse engine layout do not suffer from this. The long drive shaft adds to drivetrain elasticity. The drive shaft must also be extended for cars with a stretched wheelbase. Four-wheel drive layouts. Note: in North America, Australia and New Zealand, the term four-wheel drive usually refers only to drivetrains which are primarily two-wheel drive with a part-time four-wheel drive capability, as typically found in pickup trucks and other off-road vehicles, while the term all-wheel drive is used to refer to full-time four-wheel drive systems found in performance cars and smaller car-based SUVs. This section uses the term four-wheel drive to refer to both. Most 4WD layouts are front-engine and are derivatives of earlier front-engine, two-wheel drive designs. They fall into two major categories: front-engine, rear-wheel drive derived 4WD systems, standard in most sport utility vehicles and in passenger cars. Forerunners of today's models include the Jensen FF, AMC Eagle and Mercedes-Benz W124 with the 4MATIC system and Suzuki Grand Vitara with without 4-mode transfer case. Transverse and longitudinal engine 4WD systems derived almost exclusively from front-engine, front-drive layouts, fitted to luxury, sporting and heavy-duty segments, for example the Transverse Engine Mitsubishi 3000 GT VR4 and Toyota RAV4, and the longitudinal engine Audi Quattro and most of the Subaru line. For a full explanation of 4WD engineering considerations, see the main article on four-wheel drive. Advantages. In terms of handling, traction and performance, 4WD systems generally have most of the advantages of both front-wheel drive and rear-wheel drive. Some unique benefits are: traction is nearly doubled compared to a two-wheel drive layout. Given sufficient power, this results in unparalleled acceleration and drivability on surfaces with less than ideal grip, and superior engine braking on loose surfaces. The development of 4WD systems for high-performance cars was stimulated primarily by rallying. Handling characteristics in normal conditions can be configured to emulate FWD or RWD, or some mixture, even to switch between these behaviors according to circumstance. However, at the limit of grip, a well-balanced 4WD configuration will not degenerate into either understeer or oversteer, but instead break traction of all four wheels at the same time into a four-wheel drift. Combined with modern electronic driving aids, this flexibility allows production car engineers a wide range of freedom in selecting handling characteristics that will allow a 4WD car to be driven more safely at higher speeds by inexpert motorists than 2WD designs. Disadvantages. 4WD systems require more machinery and complex transmission components, and so increase the manufacturing cost of the vehicle and complexity of maintenance procedures and repairs compared to 2WD designs. 4WD systems increase powertrain mass, rotational inertia and power transmission losses, resulting in a reduction in performance in ideal dry conditions and increased fuel consumption compared to 2WD designs. The handbrake cannot be used to induce oversteer for maneuvering purposes, as the drivetrain couples the front and rear axles together. To overcome this limitation, some custom-prepared stage rally cars have a special mechanism added to the transmission to disconnect the rear drive if the handbrake is applied while the car is moving. Unusual 4WD layouts. From 1989 onwards, some models of Porsche 911 feature a rear-engine 4WD layout, which is akin to a longitudinal front-engine 4WD layout installed backwards with the engine at the rear of the car. From 2007 onwards, the Nissan Gtr features a front-engine 4WD longitudinal layout, but with the gearbox at the rear of the vehicle. This provides a more ideal weight balance, and improves directional stability at very high speeds by increasing the vehicle's moment of inertia around the vertical axis. This layout necessitates a second prop shaft to carry power to the front wheels. Some types of farm tractors and construction site machinery use a 4WD layout where the wheels on each side are coupled together, rather than the wheels on each axle, allowing these vehicles to pivot about their center point. Such vehicles are controlled in a fashion similar to a military tank. The Citroen Sahara had a 4WD system using complete Citroen 2CV drivetrains at both ends of the car, such that the engine at the front powered the front wheels and the engine at the back powered the rear wheels. A through-the-road hybrid vehicle uses a conventional piston engine to power two wheels, with electric motor generators on the other two wheels, giving a form of part-time 4WD. The 2005 Jeep Hurricane concept had an all-wheel drive layout that featured two V8 engines powering a single driveshaft, with a gearbox mounted in the center of the vehicle. The gears connected to two additional driveshafts, one on each side of the vehicle, that delivered power to the wheels via driveshaft joints. This was designed in order to accommodate the vehicle's unique steering system. The Ferrari Ff features a front-engine 4WD layout in which a separate transmission is used for each pair of driven wheels, rather than the more conventional setup in which a single transmission is used, followed by a center differential or viscous coupling unit to split power between the front and rear wheels. History and current use. The first FR car was an 1895 panhead model, so this layout was known as the System E panhead in the early years. Most American cars used the FR layout until the mid-1980s. The oil crisis of the 1970s and the success of small FF cars like the Mini, Volkswagen Golf, Toyota Tercel, and Honda Civic led to the widespread adoption of that layout. After the Arab oil embargo of 1973 and the 1979 fuel crises, a majority of American FR vehicles were phased out for the FF layout. This trend would spawn the SUV van conversion market. Throughout the 1980s and 1990s, most American companies set as a priority the eventual removal of rear-wheel drive from their mainstream and luxury lineup. Chrysler went 100% FF by 1990 and GM's American production went entirely FF by 1997 except the Firebird, Corvette and Camaro. Ford's full-size cars have always been FR, as was the Lincoln LS. In 2008 Hyundai introduced its own rear-wheel drive car, the Hyundai Genesis. In Australia, FR cars have remained popular throughout this period, with the Holden Commodore and Ford Falcon having consistently strong sales. In Europe, front-wheel drive was popularized by small cars like the Mini, Renault 5 and Volkswagen Golf and adopted for virtually all mainstream cars. Upscale marques like Mercedes-Benz, BMW, and Jaguar remained mostly independent of this trend, and retained a lineup mostly or entirely made up of FR cars. Japanese mainstream marques such as Toyota and Nissan became mostly or entirely FF early on, while reserving for their latterly conceived luxury divisions a mostly FR lineup. While many automakers lost sight of the true sports car, Mazda introduced the highly successful Miata Roadster in 1990, a true two-seater sports car using the traditional FR layout, which led to other campaigns such as General Motors to produce a FR sports car based on their Kappa platform. Currently most cars are FF, including virtually all front-engine economy cars, though FR cars are making a return as an alternative to large sport utility vehicles. In North America, GM returned to production of the FR luxury car with the 2003 Cadillac Quartz, and with the removal of the DTS, Cadillac will be entirely FR by 2010, and the 2010 Camaro returns as a FR sports car. Chrysler returned its full-size cars to this layout with the Chrysler 300 and related models. Despite Ford's 2011 discontinuation of the rear-wheel drive Panther platform cars, they are seeking to develop a new FR replacement. Nissan is also bringing back the Silvia to their lineup. Mazda is said to be releasing a new rotary-powered Ff car in their RX lineup by 2010, and Toyota has announced the FT86, an affordable RWD car which is the successor to the A86. Hyundai introduced their affordable RWD car, being the 2009 Hyundai Genesis and 2010 Hyundai Genesis Coupe. In the 21st century, with solutions to the engineering complexities of 4WD being widely understood, and consumer demand for increasing performance in production cars, front-engine 4WD layouts are rapidly becoming more common, and most major manufacturers now offer 4WD options on at least some models. Manufacturers with a notable expertise and history in producing 4WD performance cars are Audi and Subaru. See also, car handling, car classification, gyrocar. References